This is the first lecture over Chapter 3 for Math 107. Chapter 3 is a study of polynomials and rational functions, and we start off with mainly terminology. The term polynomial contains the word or the syllable poly, which means many, like polymer, for example. Okay, and what it has many of are monomials. And mono means one. So we'll start looking at what a monomial is. A monomial is a term. A polynomial is a function. So there's a difference right there. Okay, what a monomial is a term that consists of variables and a number, a constant, that's called the coefficient. This is a monomial. So here's your coefficient, and that term is used throughout. And then you have the variable, in this case x, and the variable can be raised to any power that is a whole number. Recall that whole numbers are 0, 1, 2, 3, etc. So it has to be, you can't have an x, for example, x to the minus 1/2. That does not constitute a monomial for two reasons. First, the power is negative, and second, it's a fraction. It's not a whole number. Okay, so this constitutes a monomial. There could be more variables raised to more powers, but in this course in algebra we are using only one independent variable, so I'm just going to talk about one independent variable. Some other examples are given in the book and in the notes. So again, this is a monomial. Everything is multiplied together. You might have 12x squared. That's a monomial. Now the polynomial is a collection of those. It is a function, so instead of saying f of x like we usually do, it's typical to write p of x or maybe even q of x, and that signifies polynomial. So it equals a sum of monomials. It could be 12x to the 5th plus 6x squared minus 3x plus 2. 2, in fact, is a monomial, and this will come up later. 2 does contain a variable, x raised to the 0th power. Okay, so it's a monomial. So here's your collection. Adding and subtracting together some group of monomials makes up the polynomial. Some polynomials you're already familiar with, but they weren't called polynomials in the past. If you had a function, for example, y equals 10, that is a polynomial. You could write it that way. It's a constant polynomial. Okay. The linear function, say 3x plus 4, that's a polynomial. 3x is a monomial, 4 is a monomial, so you could write this as a polynomial. 3x plus 4, and the other one you're familiar with are the quadratic functions. 2x squared plus 3x minus 2. And that could be written as a polynomial also. Actually, I'm not writing it in any special way, I'm just designating it as a polynomial. So here's your constant, here's your linear function, and here's a quadratic function. Okay. When we look at the polynomial, we don't always call them constant, linear, quadratic. And what happens if you have a higher, something to a higher order, such as 12x to the 95th minus 16x plus 2? Okay, what are you going to call that? Well, instead of continuing this idea of naming them, instead we go to identifying the polynomial by what is called its degree. So this is another term. And the degree is the value of the highest exponent. In this case, 95 is the highest exponent. This is a polynomial of degree 95. This is a polynomial of degree 2. For the linear function, it's a polynomial of degree 1. And this polynomial that's a constant is of degree 0. All right, so look at the highest exponent that you have in your polynomial, and that gives you the degree of the polynomial. Now, if you recall from the previous slide, when I said that the number that multiplies a variable in a monomial is called a coefficient, we use that term here as well. So, of course, that's kind of playing double duty there as a coefficient and the constant. Right now I'm highlighting in yellow the coefficients in these polynomials. It's the number, including the sign, that multiplies the variable. And again, the term for that is coefficient. Okay, so this polynomial here has a coefficient of 12 minus 16 and 2. It is of degree 95. We also identify the term with the highest exponent, and we call that the leading term. The leading term is 12x to the 95th, and the leading coefficient is 12. The last term, if there is a term that's constant, then we call that the constant. Here the constant is plus 2, here it's minus 2, here it's 4, here it's 10. So here are the words again. Oops, no pen. Monomial, and that's a term, the terms that make up the polynomial. Polynomial, again, is a function, where monomials are terms. The polynomial has a degree equal to the power. The exponent of the highest exponent of the variable in the polynomial is the degree. All the numbers are called coefficients. The term associated with the highest coefficient, or the highest, exponent, is called the leading term. And the coefficient in that term is called the leading coefficient. For example, if I have p of x is 25x to the 6th minus 6x to the 5th plus 3, let's say, then this is a polynomial. You see each one of these are monomials. They're strung together with plus and minus signs. This polynomial is of degree 6 because that's the highest exponent. The coefficients are the 25 minus 6 and 3. The constant, I didn't write that in the list, is 3 plus 3. The leading term is 25x to the 6th. And the leading coefficient is 25. The use of the word leading makes sense when you note how I've written this polynomial. It's important to write the polynomial in some kind of organized fashion, and you usually write them either in ascending order or descending order. This is descending order because I wrote the highest, the term with the highest exponent first, x to the 6th. Then I wrote the term with the next highest, x to the 5th, and then I go down, and of course a constant, which is essentially multiplying x to the 0, is written last. That's descending order. To write it in ascending order, I would start with the 3, but still I would have that organization. I would go 3 minus x to the 5th plus 25x to the 6th. It's better not to mix up the different monomials with different terms, to organize them like that, and we're going to use descending order. So of course if you use descending order, it's obvious that the leading term is the first term, and so the word leading makes sense. Now if you remember, there were general ways to write all those functions that we had before. For example, the general form for a linear equation is mx plus b. So we use letters for the coefficients, and they have some kind of meaning to us. For the quadratic, it was ax squared plus bx plus c. If it's constant, you might write y equals c and then later on give it a value. So those are general ways to write equations, and we're used to those. Now when it comes to polynomials, we also have a general way to write them, but we want to write in such a generality that we can we'll be able to handle exponents of any order, any degree polynomial. So to do that, we just specify that the highest term is going to be n. Of course, if the n is, say, 30 and we're using ABCs, we're going to run out at 26. Then you could try to use some Greek letters and it gets to be a mess. So what we're going to do with all the coefficients, instead of naming them A, B, C, or M and B or C, we're going to name them all A's. But we'll have to use subscripts to separate them. So here is a general form. I'm going to write the general form for a polynomial of, say, degree 4. So y, and p of x, of course, is just another, the function notation is just another name for y, is equal to, and all my coefficients are going to be a, but I'll give them a subscript that is the same as the power of the variable that it's multiplying. So a4, 4 is just a counter. This 4 is just a counter. The 4 on the x, of course, is a power. So that's the first term, and then, whoops, and then a2, which multiplies x squared, then a1, which just multiplies the x, and the last term, the constant, is a0. Of course, some of these could be 0, like that. Any of the a's could be 0 themselves, so you might not have all the terms present, but this is the general way to write it. As you see, I wrote the 4 down here on the a because it's multiplying a to the x to the 4th. Write the 2 here because it's multiplying x squared. So that's a general form for a polynomial of degree 4. Okay, I'll write another one for polynomial of degree 5, and then I'll do it in general because by that time you'll probably be used to this. Okay, all the polynomials are going to be a's. Sometimes you use b's if you have two polynomials in an equation. You might use a for one of the polynomials and b for the other coefficients in the other polynomial. So here's the highest term is going to be x to the 5th, so I write the coefficient as a and put a subscript 5. Just means the 5th one. A to the 4th, it multiplies the term x to the 4. And then we just keep going down. Again, we're writing in descending order. And now we want to do the same idea, but we don't want to specify the 5 here or the 4 here. We want to have a most general form for any polynomial. So I'll do that on the next slide. So here's the general form for a polynomial, and this you have to write on the test, and you write it just like this. And the reason for having you write things like this is not just idle memorization. It's because this is how people communicate. It's sort of like knowing the spelling of something or the pronunciation of something. Okay, so the first term, I don't know how big this polynomial is going to be, so I'll just use an n here. So this will have a subscript n. Now the next term is just going to be one less. For example, if n was 6, the next term would be x to the 5th. So I don't know what it is, but I know it's one less than it, so I'll just keep using that n, a to the n minus 1, and this would be x to the n minus 1. That means whatever I filled in for n here, I subtract 1 from, and that's what I'll use for the next exponent. I'll just keep going down, n minus 2, x to the n minus 2, and I don't know how many terms there are, so I'll write plus, and then I'll write the ellipse, the 3 little dots, meaning keep going in this pattern. And finally, I'll end up with an a2 times x squared, right? And then there'll be an a1 times x, and then a0. So that's the general form for a polynomial. The a's denote the coefficients. This is a polynomial of degree n. The leading term is a to the n, x to the n. The leading coefficient is a to the n. The constant is a0. I'd like to say a few words about why we study polynomials. One reason we study them is that they're easy to study. The domain of a polynomial is all real numbers. That makes it easy. the polynomial graphs have some property of them too. They're also smooth and they're continuous. And it's very nice to work with things that aren't jumps, and all you say, well, we just do something because it's easy, doesn't make a lot of sense. But on a practical side, many physical processes behave like polynomials. If you look at how, for example, braking distance varies with respect to the speed of the vehicle, it goes as x squared. It actually behaves like a polynomial. So many things act like polynomials. If you have data, a lot of data points, you don't want to deal with all those little points. What you can do is approximate the data. You can draw a line through the data or close enough to the data so that that line is a polynomial. You model that data using a polynomial. After that, all you have to do is worry about that equation. You don't have to go back to the actual data points except to check your work. And if you have a function, say, not especially data points, but just have a function, and say it's it could be something transcendental like a sine wave or exponential or some combination of them, or maybe even a function that isn't very smooth, has got corners and cusps in it. It's frequently done that those kind of functions are approximated by polynomials, because a polynomial is easy to use, and if you use enough terms you can get very, very close to the actual behavior of that function or the data. You'll see polynomials all the way through engineering, physics, math, every place. They're very general functions and they're very useful. The degree of the polynomial is more than just an identifier. It also gives information about the polynomial. And one thing we're always looking for in polynomials are the roots, the places where the polynomial crosses the x-axis. If we had a linear function, remember we looked at the x-axis intercepts. When we had a polynomial function, we looked at the roots. Right? So when you get a higher and higher order polynomials, yes, there's going to be turning points, all kinds of things associated with them, but we always are looking for the roots. We're looking for the values of the x that will drive p of x, or at which p of x is equal to 0. If we know the degree, we know the number of roots. Remember, a quadratic had 2 roots, and a linear equation had one place where it crosses the x-axis. A polynomial of degree n has n roots. Some of the numbers might be the same, there might be some complex numbers in them, but there will be n roots. And because of the continuity of the polynomial, if it goes through, say it crosses the x-axis here and here, it has to go around nice and smooth and turn around and come back down through that other x-axis crossing, or of course it could go the other direction. And then there's some other things it can do, but basically it has to turn around. Instead of calling these vertices like we did with quadratics, we just call them turning points. And the maximum number of turning points that a polynomial can have is n minus 1.